So I've talked a little bit about Newton's first law and a little bit about Newton's third law. The law that we haven't talked about yet is Newton's second law. And Newton's second law is actually very similar to Newton's first law. I actually think Newton's first law and Newton's second law are really telling you the same piece of information, just looking at it from a different direction. What Newton's second law is saying is if net force is acting on an object, the object must be accelerating, or its state of motion must be changing. Now, the way Newton would have written this is that delta, or sum of forces, equals the change in momentum of the object. Delta P over delta T. Newton didn't think about it in terms of mass and acceleration. He thought about it in terms of quantity of motion, which is momentum, the product of mass and velocity. And Newton would have really defined momentum as the product of mass and velocity. So if net force is acting on an object, one of three things must be happening. And all three of these things in physics we count as acceleration. One is an object or system is speeding up. The second is an object or system is slowing down. And the third is an object or a system is changing directions. So let's look at a quick example problem. Here I'm going to pick an Atwood's machine, as shown on the right, and created by connecting two masses, M1, which is 0.5 kilograms, and M2, which is 0.3 kilograms, by a string. M1 is sitting on a frictionless incline that's angled at 30 degrees. And we want to determine the acceleration of mass labeled M1 and which direction it accelerates. So we know right away that this is not an equilibrium problem because it's asking us to determine the acceleration. The fact that this is a frictionless ramp would fairly quickly tell you that this can't be an equilibrium problem. And let's look at how we can fairly quickly tell this can't be an equilibrium problem. Draw the free body diagram, and well, I guess it could be. You just have to have M2 be exactly the right mass to balance with M1. It's just going to be very unlikely. So here we have the normal force for M1, which I'm going to call Fn, M1g, the weight of M1, M2g, the weight of M2, Ft2, and Ft1. So if we kind of work out our equations, if M1 is accelerating, then M2 must also be accelerating. They're connected by a string. And we can actually say something about that acceleration. If they're connected by a string, if one is accelerating at, say, a half a meter per second squared, the other one must be accelerating at a half a meter per second squared as well. So I'm going to define the positive direction of acceleration, or the positive direction of force, to be this direction, that M2 is falling, which means when I write out these equations, I'm going to define this direction as positive for M2, and that direction is positive for M1. That choice of which direction is positive is a completely arbitrary choice. I could have made it a different choice and solved the problem. All that would happen is I might get a negative sign somewhere for acceleration, which means I just chose wrong. So here's for M2, M2g and Ft2 are the two forces. They're opposite directions. And for M1, well, we have Ft1 trying to pull it up. And we have really the x component, the component of weight that's acting in this direction, which is M1g sine of alpha. Now I've done this completely symbolically at this point, and I'm going to wait till the very end to plug any numbers in. What I would really suggest to you in getting into the habit of doing when you're solving problems is get into the habit of solving them algebraically like this. There are two reasons for that. The first reason is you sometimes run into problems which are symbolic problems, where it tells you solve in terms of M1, M2, G, and alpha, the acceleration of block 1, something like that. If you're not thinking about it in terms of symbolically, and you haven't practiced this technique, you're going to get completely lost when you're actually forced to do this technique. The College Board likes to do those types of problems because it doesn't matter how good your calculator is, it doesn't matter what type of calculator you have to have the skill of algebraically solving these. The second one is it's easier to spot mistakes if you're doing it symbolically. If you're working on WebAssign and it gives you red X, it's wrong. It's easier to spot a mistake if you've solved it symbolically. Something like you added when you should have subtracted. You divided when you should have multiplied. A term just disappeared. So those are some tricks that I would definitely get into the habit of doing. One other thing that we know by Newton's third law is that the tension in the two cables are the same. We kind of talked about that in the last lesson. So probably one thing I could do is solve one of these for tension and substitute it into the other one. Again, I kind of have well, two equations, and it looks like three unknowns, but ultimately I now have three equations, three unknowns, so I can solve those equations. So if I know ft2 and ft1 are the same, and I know ft2 is m2g minus m2a, I can say m1a is m2g minus m2a minus m1g sine of alpha. And now I have an equation with just one unknown, and that unknown is a. And it actually does show you it's possible to solve this in terms of m1, m2, g, and alpha. So the way to solve this is to get everything with the a on one side and keep everything without the a on the other side. So separation of variables. We can factor out the a on that left side, and then we can divide by sum of the masses. And what I can end up with is the acceleration of block A is 0.613 meters per second squared, and it is in this direction, up the ramp. So let's extend this problem. Didn't ask us to do this, but let's say we wanted to find the tension in the cable. And you might say, well, Mr. Inman, that's obvious. The tension in the cable and the weight of M2 should be the same. And I'd say, hey, wait a second. Look at this equation here, or what we just wrote out here. That is not necessarily the case. So this would be one of those you really need to be paying attention to. That's an easy mistake to make, to say, oh, just M2G, that's tension T2, we're good to go. But it's not. And it's not because M2 is also accelerating. The net force acting on M2 is not zero. So these two forces do not have to be, and actually are not, the same magnitude. So we're going to use this equation to solve for that tension. And the easiest way to do that is to solve it out. Tension is M2G minus A, and so I get 2.76. It's actually going to be less than the weight of M2. Now the second problem that I have deals with another block sitting on a ramp. It's going to be given a mass of 1.5 kilograms sitting on a ramp that's inclined to 40 degrees. And it gives me a couple coefficient of frictions. And it wants me to know, first of all, how hard would I need to push on the block to get it to start moving up the ramp? And the second part of that is, if I continue to apply this force after the block starts moving, what is the block's acceleration? So part A is really almost an equilibrium problem. How hard do I need to push on this to overcome the force of static friction? So let's look at the forces that act on this object. Here are the four forces that act on this object. Friction down the ramp. My applied force, which I'm just going to use F as that applied force, whatever force I put on that object. Weight, Fg going down, and Fn going up. So the first thing I'm going to do is try to solve part A, which I said is almost like a Newton's first law thing. What is the minimum force that I need to apply, the minimum value of F, such that I can overcome static friction? So if we work through our equations here in the x direction, and I'm going to call up and down the ramp the x direction. I have the force I apply, I have the frictional force, and, well, the component of the weight that goes down the ramp, essentially, Fg sine of theta. And then in the y direction, and call this direction here, I have Fn, and then the component of weight that's acting down into the block. So we can find the normal force fairly quickly, mg cosine of theta. And where that becomes helpful is that I can write the frictional force in terms of the normal force and the coefficient of friction. I can also substitute mg in for weight, or force due to gravity here. So the next thing I can do is I can substitute this in here, and it looks like I can add both those terms over there. So really the force that I need to apply needs to do two things. It needs to overcome the static frictional force, which is this term right here. It also needs to overcome how much of the weight of the block is trying to push the block down the ramp, the x component of that weight here. So what we can do is we can rearrange this, and we get actually a pretty nice clean equation for this force in terms of m, g, theta, and mu s. Now if I actually wanted to calculate out the value, I could plug in my values, and what you end up with is 16.2 newtons is the force that I would need to apply in order for the block to start to move. Now what's true in part B is that once I get the block to start to move, I no longer am dealing with static friction, but this block is now sliding up the ramp, so I'm dealing with kinetic friction. So what I would generally assume, if this thing is starting to move up the ramp, in almost every case that I can think of, the force due to kinetic friction is less than the maximum static frictional force. It's harder to get an object to start to move than it is to continue to move it at a constant rate of speed. So I would make the assumption this object is accelerating probably up the ramp, the direction that I'm pushing it, because F for kinetic frictional force is probably less than F for static frictional force. And we kind of knew what F for static frictional force, or at least something we could calculate it out if we wanted to. The normal force piece of this is still the same. And in fact, the first few steps look very similar. The only difference is instead of equal to 0, I have equal to MA. And it's this A that I'm interested in. And in fact, up to here, it's a very similar process. The only thing that I've done differently is substituted in the mg in here, mg cosine of theta, and then I divided everything by m. And so there we go. We have acceleration in terms of the force that I apply, mu k, mass of the block, and g. I guess and theta. And if I actually plug those numbers in, I get 1.5 meters per second squared. So that's kind of some quick overviews about Newton's second law and some problems dealing with Newton's second law. We will definitely practice some of that symbolic practice doing problems that way, because I know that might be new to some of you, but it is something that I think you need to get in the habit of doing.